So, today we will talk about the electrokinetic transport in microfluidics. So, basically what we will be doing is on mathematical modeling for this electrokinetic transport which arise in microfluidics devices. Now, how we can say that the studies of transport process in microscales are referred to as microfluidics. Microfluidics deals with behavior, precise control and manipulation of fluid that are geometrically constant to small, typically sub-millimeter scale. These microfluidic devices have many applications. So, which we can see some of the things I have written over here. So, mostly it has the advantage is that it is portable and it require very tiny amount of samples, and also it has the capability of controlling the transport phenomena to our requirement because it can be driven by a say for example, the electrokinetic mechanisms and all these things. Now, what is the nanometer or micrometer? So, first let us know about this. So, 1 micrometer we define as 10 to the power minus 6 meter, and 1 nanometer is as 10 to the power minus 3 micrometer. So, 1 nanometer is basically 10 to the power minus 9 meter. So, obviously, this shows that it is a very small length scale we will be talking about. Now, when it comes to the small length scale, so difficulty arises that the surface area becomes the enormous surface area will dominate the situations compared to the volume area. So, that is one characteristics of microfluidics. So, that means the surface dominated phenomena are very important over here. So, for example, the surface roughness, if any is a molecular dimension roughness, say a few Armstrong, or the surface tension forces, and most important thing what we will be talking or referring here is the surface charge densities and all these things. So, that creates a important situation in the analyzing the microfluidic transport in microfluidics. Now, one of the primary initial challenges towards the miniaturization of fluidic components and the creation of microfluidic system was the search for forcing mechanism. So, what should be the forcing mechanism? Because if you require to pump say a fluid through a small syringe of say a few millimeter and all. So, how much the enormous pressure is required to be applied in order to have a volume flow through a thinner channel or thin tubes situation, capillary one can say. Now, so the pressure when it comes to the microscale, it becomes enormous and is impossible. So, what is the driving mechanism? So, most popular driving mechanism is the electrokinetic forcing. So, because electrokinetics forcing has a advantage is that it is very easy to control. You can place the electrodes in a way wherever you require how much voltage drop to be created, and also one can manipulate, direction can be changed, it can be several sophisticated way one can handle the electrokinetic mechanisms. Now, so that is why electrokinetic flow has been proposed as a convenient means of transporting electrolyte solution in such devices. Since the liquid flow is governed by the locations of impenetrable electrodes, it is far easier to control, and as I said, so this kind of things is described here. And also this important thing is that a small amount of sample is enough to analyze in these lab on a chips or microtroids devices. Now, as I mentioned before, So, this micro scale, what happens is that large surface area, so surface properties are dominating in such kind of transport phenomena. Then one of the surface induced phenomena is the creation of electric double layer. Then surface inhomogeneity, you can have different material in the surface compositions, and also say roughness of even a molecular dimension is also can change the scenario. And also in microfluidics, we will deal with the complex fluids, means it is a mixture of suspension of colloid particles, soft particles, so this kind of microparticles, so that becomes a complex fluids. And also this, since we are talking about the aqueous media or ionized fluids, so it will have the multi-component fluid is a miscible fluids. So, that is why we can say this, in this situation it will be complex fluids. Now, this electric field driving forces are two kind of situation, three kind of phenomena arises, is the electroosmosis, electrophoresis, and also the Joule heating. Because of the movement of the ions, there will be a heat generations, and that is Joule heating. We will talk later on about this. Now, electroosmosis is basically the motion of ionized liquid relative to the stationary charged surface by an applied electric field, and electrophoresis is the motion of the charged surface and macromolecules relative to the stationary liquid by an applied electric field. Now, how the surface charge develops. Now, here now we will be talking about the few things about the electrostatic phenomena. Now, this electrostatics phenomena are governed by this few principles. One is the charge conservation principle. The total charge of an isolated body cannot be changed. Then another important principle is the total charge on a body is an integral multiple of the charge carried by an electron, that is also referred as the elementary charge given by this. So, total charge will be some q into n e, where n is an integer. So, it cannot have a kind of fraction or something. Now, what happens is that when aqueous solvents or ionized fluid is in contact with a solid surface, a charge develops, static charge will develop at the interface between the liquid and fluid interface. Due to the, now these occurs because of the absorption dissociation reaction as governed by these equations, and an example I have cited over here. So, this reaction, say if the solid liquid interface is have a functional group as MH, it consists of a functional group is MOH. So, in presence of the H plus ions, and it will create this kind of ions MO minus and MOH2 plus. Now, these H plus ions are related to the pH of the electrolyte, and also the ionic concentration of the electrolyte also can influence. Now, the rate of reactions and all the that depends on the reaction constants. So, all the details I have omitted over here. So, any book, basic electrokinetics book can will discuss about this kind of reactions. So, basically what we want to show from here is how this charge is produced at the interface. So, through this association dissociation reactions, so what we have is a generation of negative ions and positive ions. So, if we denote these as the concentration, molar concentration of the charged species, then surface charge density is net amount of concentration of positive and negative ions. So, this is the way it is written, sigma s, where F is the Faraday constant. Faraday constant is basically E into Na. Na is the number of molecules and E is the electron charge. So, this is Na is the Avogadro's number. So, Faraday constant is the charge per mole of a single ionized species. So, this is the net concentration. So, it is into F, that is the way it is defined as the charge density, because it is per volume. So, per unit area. So, sigma s is the here is the surface charge density. So, we have denoted here A plus the concentration of ionic species A by this bracket, square bracket. So, obviously, this depends on the reaction constant and pH of the solution. So, this give an idea that how is surface charge develops. Now, what will happen is that when there is a say negative amount, normally these electrodes or the channel, so this interface are normally made up of SiO2 silicon dioxide kind of material. So, this will generate this will create a negative surface charge on the surface. Okay. So, this negative surface charge, what it will do is it will attract positive surface charge, positive ions from the debye layer, sorry, not debye layer. So, now, if I show in this figure, so this is the surface charge develops, which is negative, and it will attract positive ions from the aqueous media. So, there will be a situation like this way. So, then this positive will attract negative ions, and in that process there will be a layer near the surface, where there will be a more number of unbalanced charge ions compared to the bulk or core region. Now, this layer can be divided into two. One is very close to the surface, that is the one is referred as the Stern layer, and this dimension of this or length of this is of molecular dimension few Armstrong, and there is another layer above which is the diffuse layer, where the ions are loosely attracted, loosely connected. So, it can mobile. Okay. So, this is referred as the diffuse layer. So, in total this is referred as the electric double layer or debye layer. Debye is the scientist who first discussed about this. So, this total is referred as the debye layer. Another important thing is that the potential drop from the surface to the edge of this debye layer is also called the slip plane. So, it is referred as the zeta potential, okay, as it is drawn over here. Now, what will happen is that since the ions are mobile over here, so if some external mechanisms is applied, so if there is an external mechanism applied, so okay, whatever was here. So, then what will happen? These positive ions will get attracted to the negative electrodes. Say, so if I apply a say if I take a cathode anode here and there is a cathode here. So, let us call this as anode, this is cathode. Now, so this is the debye layer. So, now if there is a voltage electric field is applied, that is creating a voltage drop. So, this in the debye layer, whatever the surplus positive ions, it will be attracted towards the negative electrodes, and when it will be have a Coulombic attractive force. So, and in that process it will generate a flow over within this, because it will drag, it is inside the liquid media. So, it will drag the fluid along with them, and there will be a flow generation. So, this is basically is the principle of electroosmotic flow in a say capillary or channel regions. So, under a electric field, so here we are the driving mechanism is the under an electric field, and basic principle is the formation of the debye layer at the charged surface. Okay. Now, so we are intended to do the modeling of this kind of situation. So, before that we have to understand the electrostatic terminologies and the how we quantify the effects of charges and other things. So, first we talk about the Coulomb's law. So, suppose there are 2 point charges q and q dash are placed at a distance, separation distance say by r, and in a medium which have a permittivity epsilon e, then the force interacting force between this q and q dash is governed by this equation. This is called the Coulomb's law. Okay, r is the separation distance. Now, we define the electric field at any point as the force per unit charge on that point. So, at this, if I consider the q is now at the origin, so the electric field we can write as this force per unit charge and given by this way, which I can consider in a vector form if I take the radial vector as r by this one, this equation, equation 1. So, now this is the epsilon e is defined as the permittivity of the medium. Now, before we talk about the permittivity, so now permittivity roughly we can say is the resistance created by the medium to the electric field. So, if it is in vacuum, so we would have had the same electric field, and if there is a medium in between the space on which the charges are placed, so that has created a resistance which is measured by the permittivity. Now, this force can work, so can perform work. So, the work W, if I say in dragging a unit charge from point A to point B, so that can be written as F dot dr. Basically, here it should be, if I write in a vector form, it is F dot dr. So, this is equal to E dot dr. So, what we get is by integration is this term, equation 2. Now, if I consider that the point is at infinity, so and then I define this as the potential, electrostatic potential phi x y z in the work from dragging the point charge from infinity to a point x y z. So, under an electric field due to a charge q which is placed at the origin is given by this. So, this we call as the electric potential created by the electric field by defined by this way. Now, if there are number of point charges at different positions r I, if I call the position vectors, and q I are the number of point charges. So, then the electric potential, the combined one will be in the same principle we can write is this way. In fact, we can generalize to the Coulomb's law for finding the force by summation of all this Coulombic inverse square law form, and we get a charge electric potential governed by this equation. Another important thing from here, you see the work done by the electric interacting force, electric force is independent of the path joining between the 2 points A and B. So, it is a material of how you connect the 2 points A and B. So, that means this is a conservative field. Conservative field means we can write that this is equal to minus grad phi, where phi is a scalar quantity, and also which shows that it is a irrotational. That means, curl of the electric field E at any point is 0. So, this suggests that we can associate a scalar quantity phi, which we have already defined as a gradient of phi, we can refer as the electric field, and this is a minus because that if I represent in terms of work, so that minus appears. So, in every point on the space we have always that electric field as irrotational. Now, permittivity, how we define the electric permittivity. Now, electric permittivity is a case. So, when you have a medium over here, so suppose you have two charged plates, positively charged and negatively charged, and there is a medium, and so there will be an electric field will be generated. Now, this medium is composed of some water or something, so that will form a dipole to oppose the medium is made up of molecules, of course. So, they will form a each molecules will form a dipole to oppose the electric field. So, that means you will have a situation as this kind of things, minus plus, they will arrange themselves. So, there will be a electric field induced by these dipoles, which opposes the electric field developed by these charges. Okay. Now, so obviously, the electric field whatever generated by these charges are not the same. So, and it depends on what type of medium you are considering. So, normally this the permittivity is represented as epsilon 0 into epsilon r. Epsilon 0 is the permittivity in the vacuum, and epsilon r is the relative permittivity of the medium. And this epsilon r are greater than 1, and epsilon r can be defined as the force when two charges, point charges are placed in vacuum. So, whatever the force that 2 point charges experienced, and now if I place these point charges in the medium, so whatever the force they acquire, so that is what is written over here. So, at the same separation distance. So, that is the thing is referred as the electric permittivity. So, obviously, electric permittivity is always will be greater than equal to 1. So, for gas or air we can have the permittivity as 1. For water, this is the permittivity is generally taken. So, that means that vacuum electric permittivity should be multiplied with the ratio which is dimensionless. Now, what I was just talking about. So, this is the thing is written in a better words over here. So, this is the way we define the permittivity. So, obviously, it shows that the electric field whatever is developed in a region in a medium will be lower compared to the electric field developed in the vacuum. Now, what we need to have a situation to get a equation for the electric field. Now, one of the law is the Gauss law, which gives the electric field into enclosed area. This is basically the way one can say define the Gauss law as the charge enclosed by the area. Now, suppose you have a charge, point charge as q, which is at the some point origin say. So, let us construct a sphere of volume V enclosed by a surface S of radius capital R. So, now we measure the flux of the electric field. The electric field will be generated by the point charge. So, the flux of the electric field will be measured by the surface integral E dot n ds. Okay, n is the outward normal to the surface. Okay. So, n will consider as the outward normal to the surface. So, E dot n ds is measured over the whole surface area is measured the flux. So, that the electric field what we have defined already. So, this is the surface area, because as R is fixed R equal to capital R. So, you get the flux as q by epsilon E. Okay. So, now this integration, now if you have number of charges apart from this q. So, that can be we can generalize this thing as the sigma of q I Now, if we apply the Gauss divergence theorem, that means we convert the surface integral to volume integral. So, what we get is this situation, that is we convert in the surface integral to the volume integral given by this way. So, that is the now there is the divergence of E dV equal to, now this is the integrated over the whole volume. So, this rho E is called the volume charge density. So, this gives you, now what we have here, sorry, I should have shown the here itself. Now, V we have choose arbitrary volume which is enclosing the charged. So, and the rho E is the volume charge density, whatever the net amount of charge within the volume. So, that is because it is integrated as a volume integral. So, V is arbitrary and this is happening for any choice of V. So, we can write this as this form, minus epsilon E del to phi equal to rho E, because if I write the divergence of E equal to basically this is grad phi, already we have defined what is the we have already is rho E, what was there, rho E epsilon. So, there was a epsilon over here. So, now what we have is that is equal to del to phi equal to, there is a minus. Now, minus will be here because this is the E equal to minus grad phi. So, you get this relation. So, what I find is that del to phi equal to minus rho E by epsilon E. Epsilon E is the permittivity of the medium. So, we get a relation for the electric potential with the volume charge density. This equation is referred as the Poisson. This is the Poisson equation, of course, non-homogeneous Laplace equation. So, this is the Poisson equation and this governs the electric potential. So, that is why this is the Poisson equation for the electric field. Okay, so, next we will talk about the transport of transport equations for electrokinetics. Now, in the aqueous media or ionized fluid, what you have is a ions are dissolved in the medium. There may be some are dissolved or there are multi-component situations, because the for example, H2O and NaCl solution. So, after dissociation you will have Na plus and Cl minus ions and the uncharged H2O molecules and all. Now, if there is a electric field as we discussed before, so there will be a flow generated, then the ions will also experience electrostatic force because of the Coulombic attractions and all. So, that way there will be a transportation of ions. So, this transportation of ions will create an electric field. So, we need to know the how the distribution of the ions. Now, as well as we need to know the fluid flow also. Now, first we talk about the equation for fluid flow. Now, how it is connected. Now, here you are considering a fluid which have a charge density rho E. So, because of the presence of this volume charge density rho E, so the fluid, if we consider a volume element within the fluid, so fluid will experience a force, electrostatic force, which is also governed by the Lorentz relation, is governed by this rho E. E is the electric field at that elementary volume. So, this is the electric body force will be experienced by the fluid elements is covered by this rho E E. Now, so that means we cannot isolate in this situation the transport of fluid from the transport of ions.